Okay, so the first question asks you simply what happens to a molecule when it absorbs infrared radiation. And the answer to that, in terms of what you write down, is simply that it causes vibration of covalent bonds. Okay, so that's, you've got to make sure you specify covalent bonds, and that word vibration is crucial. But it's a kind of strange concept, because you may well be used to sort of thinking of a covalent bond as a sort of very much a fixed thing. So, you know, if you have, I don't know, a carbon bonded to a hydrogen, you think of them, because of the models and all the diagrams we draw, as sort of locked together at a fixed distance. But in fact this isn't true. A bond is more sort of like a spring. So it has, if you like, a sort of minimum energy distance, but it can vibrate around that. And in fact bonds do vibrate all the time, because of a curious quantum mechanical thing called the uncertainty principle. It's actually impossible for bonds to sit completely still. So even when you go down to the lowest possible temperatures, they have what's called a 0 point energy, which means they're vibrating a bit. But by the time you bring in some extra energy in the form of an infrared photon, it can take them to a higher vibration energy level. So if you like, it makes the bonds vibrate more. But you don't need to get into all that detail. So just to sort of give you an example to help you sort of picture that a little bit more, imagine a carbon dioxide molecule. So if I'm the carbon in the middle and these are the two oxygens at the side, there are actually three ways that a carbon dioxide molecule can vibrate. So the simplest one is that it can do this. So this is called a symmetric stretch. And what it means is that the two CO bonds shrink and expand and shrink and expand, and they do that in sync with one another. And that's one type of vibration. Now that particular one actually can't be excited by infrared because of weird things to do with symmetry that we don't need to worry about. But there are two other types of vibration that can be. So the first is this one. So this is called an asymmetric stretch. Okay, so as one carbon-oxygen bond is lengthening, this one is shortening, and they do that like this. And that one can be excited by infrared radiation. The third one is this, which is called a bending vibration. So in this case, actually, instead of the bonds lengthening and shortening, the bond angle changes. And again, it can do that in a sort of vibrating way like that, so that it just keeps coming backwards and forwards. Now the important thing is that each of those kinds of vibration that requires a very specific photon energy to be excited. So you're used to this idea with electrons, that electrons require a very specific amount of energy to go up, say, you know, from a 1s orbital to a 2s orbital, because they have defined energy levels. And it's the same with vibrational levels. So that a very specific photon energy is required to excite any particular kind of vibration. So if you draw a graph of something like percentage of the infrared absorbed as a function of the wavelength of the infrared, what you find is that that's very dependent on the wavelength because of these specific energy levels associated with each vibration. So if you do that for carbon dioxide, you actually get two peaks. Something like that, because of the two different kinds of vibration that could be excited, as say the symmetric one you don't see. So what that corresponds to is a specific wavelength, and therefore a specific photon energy is required to excite each kind of vibration. Now, one of the things that you need immediately to get used to is that although you might think of that as the sensible way to plot a infrared spectrum, that's not what you actually do, because the people who invented this decided to do it differently. So let's have a look at what an actual infrared spectrum might look like. So the first thing is that instead of wavelength, they use wave number, which is actually equal to 1 over the wavelength. And therefore, instead of having units of centimetres, which would be the sort of range of the wavelength for infrared, it has units of centimetres to the -1, because it's 1 over the wavelength. And you don't need to know the definition of that. You don't need to worry about why that's done. It's just really for historical reasons. But that's what you'll see when you look at spectra, is the wave number there. And the next thing they do that's weird is that you're used to, normally on graphs, the numbers will increase across this way, but the wave number axis increases that way. So when we're looking at organic compounds, the typical range we look at goes from about 500 wave numbers up to about 4,000 wave numbers. That would be a sort of typical spectrum. So it's increasing that way. And it seems really weird to start with, but you quickly get used to it. But you need to be careful, because, you know, if this is sort of 3,000 here, and you see a peak there, you have to be careful not to think, oh, that's slightly less than 3,000, because of course, because we're going this way, it's slightly more than 3,000. So that's something that does take a bit of getting used to. Now on this axis, they do measure how much of the infrared is absorbed, but again, just to be different, they do it upside down. So absorption goes that way. So what that means is that you have a baseline at the top corresponding to 0 absorption. And then when you come to a wave number which corresponds to an energy which can be absorbed by the molecule, then you get a peak that goes downwards. So you get something that looks like that. So again, it's important to get used to the idea that peaks point downwards, and so this is the wave number corresponding to the top of that peak, and so on.